Hello, welcome to another organic lecture on carboxylic acid derivatives. Today we'll be talking about esters, right? Esters. So if we look at our ester, we have a carbonyl directly attached to an oxygen, directly attached to some alkyl group there. That's going to be our ester. Now, as we saw with our carboxylic acid chlorides and things, reactivity is going to be slightly different based on what this group is that's attached to our carbonyl. And so we'll look at some reactions and some of the chemistry we can do with this group, right? Some of it will be somewhat similar to the carboxylic acid, the acid chloride, based on this idea that this is actually okay leaving, not too bad, right? It's comparable. Not as good as the chlorine, but not as bad as an OH group here. So it's kind of in the middle. So we can use it for some reactions that we've done before, okay? And so we'll go through the process of doing some of these reactions. Again, some of them look very similar to our acid chlorides, and then we'll try to look at some new ones as well. All right, so let's look at a simple one we'll start with. I can take this group here, and I can, after that, I can react it with what? I can react it with NaOH. Right, and already we know NaOH, so in positive, that means our oxygen is going to be negatively charged. So what do you think is going to happen here? What do you think is our OH going to do? That negatively charged OH, what's it going to do? Can be very attracted to something very partially positive, right? Which would be like our carbon. Go up like that. OR here. And we get to this species here, right? We get this tetrahedral intermediate. What do you think is going to happen now? As the electrons come back down, we're going to kick off a group. Now, remember, we talked about the OH group not being a very good leaving group at all, right? Very bad. But compared to this OR group, this OR group is actually going to be a fairly good lead group compared to the OH. So that means that this OR group is going to be kicked off. And we get to this species here. Remember, this group is very basic. So what's it going to do? It's going to pull off this proton. And we get to the carboxylic anion, right? Now, if we want the carboxylic acid version, what do we have to do? We're going to have to throw in a little bit of acid in to protonate that if you want to do that reaction, right? We got to protonate. But we can see here for this mechanism, OH is going to attack the carbon-carbonyl. Electrons come up. Electrons come back down. We're going to kick off the OR. And the OR is basic enough, it's going to pull off the hydrogen and generate this carboxylic anion there, right? To make the anion, right? So that's our first reaction we can look at, right? And as we go through here, we can look at other types of reactions, right? That we can do with this type of starting material. So let's look at some other reactions. So we looked at a base reaction using base. So we haven't done anything with acid in a while. Let's do an acid reaction. And we'll just do this acid catalyzed reaction here. So we're using acid. What do you think is going to happen? Now, we've seen these reactions before in the past, right? Where we have a acid in there, and we have our carbonyl here. What was the first thing we've done with all those reactions, right? What was the first thing? Just like we saw in the past. We get to this species here, where what? We have an oxygen with a positive charge on it. What do you want to do now? Well, electrons move up, resonance. And we generate that positive charge there. Now we have this positive charge. What do you want to do now? We have water in there, so let's go ahead and let's attack it with water. Remember, we have a carbocation here. Now we can attack it with our weak nucleophile, water. And we get to the species here, right? Very similar to what we saw before, right? We've seen these before. Oxygen has a positive charge. We don't want oxygen to be a positive charge. We actually want to make something made into a better leaving group. Because right now, this group is way better lead group than the OR, so this group would come off. But we want to do something. We want to lose this proton. Maybe we can do something like what? How about a proton transfer? We've done those before. Right? We get to this species here, where now we have what? Now we have this positive charge on the oxygen. The oxygen is drawn very, very small. Bigger. Now we have a positive charge on the oxygen. What's going to happen? It's going to now leave. Now it's a really good leaving group. We have this positive charge here. What do you want to do now? As we've seen in the past, we want to do our resonance. Right? We have this, now we've done resonance of it. Now we see our carbonyl again, which is great. And now last step is what? We're going to lose that hydrogen. Remember, it's acid catalyzed, so it's got to get the hydrogen back to the water. And so with this acid catalyzed reaction, right, where we're able to take our ester and under acidic conditions with water, we're able to then convert our ester back to a carboxylic acid. Okay, back to a carboxylic acid. Again, very simple mechanism that we saw before, right? Protonate the carbonyl, electrons move up, carbocation, water attacks, proton transfer, group leaves, resonance structure. Get that resonance structure again, right? And then we have, we get our positive charge in oxygen, pull out proton, generate our carboxylic acid, right? Very similar mechanism we saw with our aldehydes and ketones, very similar, right? So this is what we can do with our ester under acidic conditions with water, right? So let's look at a couple more reactions with our ester. All right, we take our ester, and we have two ways now to turn it into a carboxylic acid, right? Either under basic conditions or acidic conditions. Let's look at our ester with now, we can look at it now with lithium mineral hydride. All right, this is going to be excess. You can imagine this is going to be a very similar reaction that we saw before, right? Very similar reaction. You can kind of guess what we're going to form. Very similar that we did before, right? Where I can take this group here, again, it's in excess, right? And you can see here what we're going to do. We're going to get back to our primary alcohol. Very similar mechanism. You'd be bored by this. You might even want to fast forward past this. Look at this species here. Carbonyl is going to come back down, and now we can kick off this group. Because again, relative, this is a way better leaving group than the hydrogen would be, right? Way better leaving group. So I can leave. And we're back at our aldehyde. Again, aldehyde with lithium hydride, it's going to react again. It's going to. And look at that. Now we have those two hydrogens attached, right? Both of these hydrogens came from our lithium hydride. Last step is what? Addition of our water. All right, so it takes us back to our alcohol, right? We get a primary alcohol. Because again, having this good lead group here, relatively good lead group, we're able to add lithium hydride twice, right? Really, it's about that being a good lead group. If it wasn't a very good lead group, that would be more of an issue, right? Okay. So this is with aluminum hydride. What about with the Grignard reagent? What can we see with the Grignard reagent? Let's look at that. Again, with the Grignard reagent, it's the same reaction, same mechanism we saw with our acid chloride. So we're not going to spend much time on this one. Like before, excess, and we're going to end up with alpha-C R1. So we need addition of 2 R1s there, right, to make our alcohol, right? Tertiary alcohol, right? Tertiary alcohol. So that's the reaction we do with the Grignard. I won't go through the mechanism again because we've done this mechanism already. So I don't want to keep doing these mechanisms over and over again. They're very similar, right? Very similar result from the acid chloride, same mechanism. Okay? But I do want to do one more reaction for you. Is if I take my ester, now react it with a new reagent, diol. Okay, diol with my reagent. We're actually going to take our ester and we're actually going to stop to an aldehyde, which is pretty nice. So diol is a mild reducing agent. Okay, so think of diol again as being giving off that hydrate, but it's a very mild reducing agent. So we're only going to give off one. It's not going to be as reactive as the other ones, right? So for this reaction here, for the mechanism, and I won't draw the whole structure of diol. It's a fairly large structure. So then people abbreviate it like that. I'll put a hydrate out there just to show that's where the hydrate's coming from, right? But I'm not going to draw the whole structure of diol. We just got to recognize it's a mild reducing agent. A lot easier to remember 5 letters, right? And so the same thing, the hydrate is going to attack here, come up. R here, and then we have electrons coming back to that, right? And we get it. We kick off, electrons go back down, we kick off our lead group, which is OR, and we end up with an aldehyde. So what's nice about diol is an easy way to go from an ester just to the aldehyde. Say you want to get just an aldehyde, we can do that now, right, using diol. Diol is going to be our mild reducing agent, right? It's our mild reducing agent. It does the same thing, gives off a hydride, but again, it's not as reactive. We're not going to use any hydrides off, right? Just give this one. That's not very reactive. Gives it off, does addition once, and that's it. Stops there, okay? So that's with our diol. Okay? So with our esters, we did 1, 2, 3, 4, 5 different reactions. I think we did some reactions with this one. We did some acid chlorides, very similar to the acid chlorides. As we move forward to carboxylic acid and to the amides, we won't do as many. We'll get less than this. But notice what we got to keep track of. There's a lot of different reactions we're kind of throwing out, right? A lot of us similar mechanisms, but we have to know these reactions. I have to know if I take my ester, I react it with something, what I'm going to get, right? This will help us later on, right? As we start doing more things together. Okay? So keep track of these reactions, write them out, and keep them all.